Okay. I hope you had a good break. So we can continue now. Now, before the break, admin, can you hear me?
I can hear you, sir.
Admin, can you hear me?
I can hear you, sir.
Okay, good. Okay, good. Now, before the break, we learned some few things. Number one, we must revert to first principles if we want to advance our knowledge. We cannot advance crammed knowledge. You can't cram something, cram another one, cram another one, cram another one. You must always go back to the first principle. So you must know the meaning of this statement, that there's a limit means that for any pre-assigned real number, any pre-assigned positive number, no matter how small, we can always make the thing on both sides of the limit to be closer than that number if we want to. And all we need to do is to move close to the point of the limit. That's all. If you understand what this is saying, you can now understand how anything can be differentiated with anything at all, because it is this law that we're going to look at. If we are going to make any modification, we are just going to generalize this, that it will no longer be talking only about scalars and scalars, scalar functions or scalar arguments. It can talk about any kind of function and any kind of argument. At least you know that apart from scalar valued function or scalar argument, we can have vector valued function or scalar argument. We can also have tensor valued function or scalar argument. But we turn it around. We can have scalar valued functions on vector argument. An example is magnitude. Magnitude is a scalar valued function, but the argument is a vector. You can also have the magnitude of tensor, which is a scalar valued function whose argument is a tensor. Now, if you now want to differentiate with respect to that argument, then you have problems, because all your concept of limits and differentiation require the concept of limit and the concept of differentiation require division with respect to the argument, and you cannot differentiate vectors or tensors. And that is what necessitates moving to something else. But before I go on, let me just remind you what first principles mean. And to get you what first principles mean, where I'm going to show how to differentiate y is equal to x squared from first principles. I know you know it. I'm not doing it because you don't know it. I'm doing it to remind you so that you can take note of some steps, so that you do not accept anything but cram it, so that you know that every step of the way is clear to you. And you can ask questions if there's any step of the way that is not clear. So I know I'm not introducing something strange or new. So let us go. Before we do that, I say, are there tensor valued functions of tensor arguments? Yes, plenty. An example is the cofactor of a tensor. It is simply the tensor inverted multiplied by a determinant. So once you know the tensor, you can invert it. You can invert the tensor, take the transpose of the inverse and multiply it by the determinant, and then you have a new thing. And this is a function. And this is a function of the original tensor, and it is tensor valued. It's possible to have a tensor valued function of a tensor argument. It is possible to have a tensor valued function of a vector argument. And everything is possible. But the only ones you can differentiate right now are things that have scalar arguments. That's the only thing your calculus can do. When the argument is no longer scalar, your calculus is powerless. And that is what we want to do. But before we do that, I want to remind you of some things you knew before, just to re-emphasize them. First principles. So this is the formula for derivative from first principles. If you want to find the derivative of a function y at a point h, it is, sorry, at a point x, you evaluate it at a nearby point by adding an h to the point, subtract the value at x, and then divide by h as you allow the h that you are using to become smaller and smaller. This formula applies always. It doesn't matter what the function is. It doesn't even matter whether the function is continuous or whatever the function is. This is a formula that will always work. And since the advent of computers, even if it is laborious to manually calculate this, computers can calculate them. In fact, that is the whole area of numerical analysis. You go back to first principles and you use computer to take over the drudgery. So all those cram have died because you do not need to worry about tedium and repetition any longer. The fact that something is tedious and laborious doesn't mean you can't do it, because you can always program a computer to do it. So let us look at it. If y is equal to x squared, you evaluate it at x plus h. So you evaluate x plus h squared minus x squared. Open that bracket, you have x squared plus 2xh plus h squared minus x squared. When you cancel this x squared plus 2h, it remains 2xh plus h squared over h. And because the limit of the sum is the sum of the limits, so 2xh over h is simply 2x, and there is no h left, so the limit is no longer important here because h has vanished. And then you now have h squared over h, which is the same thing as h. The limit at h tends to 0 of h is 0. So the answer is 2x. This is the reason why, before you started cramming, this is the reason why the derivative of x squared is 2x. Not because you know that we just reduce the power by 1 and multiply it in front. That is a formula. It is not the definition. This is the definition that we always work. That your formula works only for powers. If it is, you cannot do that for sine x, but the first principles will work. You cannot do that for exponentiation. The principle will work. And all the other functions, you can't use this method. Principle always works. That is the thing. It may be tedious, it may be laborious, but it will always work. Let us go to the next example. Suppose y is equal to sine x. Again, you start, again, this formula will always work. So y of at x plus h is sine x plus h minus sine of x. And all you need to remember is how to expand the sign of the sum. That is sine x cos h plus sine h cos x minus sine x. So sine x is common to these two. So you put sine x outside, cos h minus 1 plus sine x cos h. And the limit of the sum is the sum of the limit. So these two go. So you can carry this sine out and you can carry this cos out. So you are now left with evaluating the limit as h tends to 0 of cos h minus 1 over h of sine h over h. Now, here is where your teacher in secondary school might have tricked you. If he doesn't understand what goes on here, you will just say, accept that this is 1 and this is 0, and you accept it and cram it. I'm not going to do that to you. I'm going to show you that you can actually know what the values here are. You can know. For instance, we've already established. Let me ask a question here, if anybody remembers. Do you remember sine x divided by x in the limit as x tends to 0 is 1? Do you remember that? If you don't remember, tell me. Oh, you remember. Okay, you remember that. You know, we did that in this. Okay, so no, I don't need to worry about that one. Good. No problem. Okay. Now, I want to ask, do you remember that cos h minus 1 over h in the limit is 0? Do you remember that too? Cos h minus 1 over h. Where did you remember it from? How do you know? Cos h minus 1 over h, that the limit as h tends to 0 is 0. Is there anybody who doesn't understand that? Who doesn't know that? If you don't know it, I will show you. So I'm not going to blame you. I'm not going to curse you. I'm not going to abuse you. I will show you. Is it obvious? If it's not obvious to you, say so now. No, I'm talking of this one. This one. That is that cos h minus 1 over h, the limit as h tends to 0 is 0. The limit of cos h minus 1 over h as h tends to 0, then the limit there is 0. Okay, somebody says you can use L'Hopital's rule. Okay, good. In L'Hopital's rule, you differentiate. If you differentiate the down there, you have 1. If you differentiate the forward there, you have cos. So you have 1, then you have sine h. So it is now the limit as h tends to 0 of sine h. Good. So somebody that is James Udotong. You can use L'Hopital's rule because if you substitute 0, you have 1 minus 1, that is 0 over 0. So L'Hopital's rule can be used. Okay, good. So somebody said we can use L'Hopital's rule. Anigbo said it's not obvious. Somebody says, why is that? Okay. Now, if you don't want to use L'Hopital's rule, let us attack it directly without L'Hopital's rule. Let's attack it directly. So what is the limit as h tends to 0 of course h minus 1 over h? Here is something you accepted from a teacher or lecturer without necessarily understanding. That limit is 0, and we can see it without needing to evaluate the quantity itself as 0. So how do I do it? Just go to your spreadsheet, tabulate h. Tabulate cos h. Then find cos h minus 1. Just subtract 1 from this one. And then do the quotients. Divide cos h minus 1 over h. And see whether it tends anywhere, whether it has a limit. If you cannot see it with the numbers, I plotted it here. So it is going from here, going down in a straight line. If you omit the point of h is equal to 0, it will go. Do you need a prophet? Do you need a babalawo? Do you need anybody to tell you that this unknown thing here will be 0? It is obvious. Just look at it. Look at the numbers. Look at where they are going. They are going straight to 0. It is minus 0.005 here. It's plus 0.005 here. So that's it. You don't even need you see, this method of using a spreadsheet will always work. L'Hopital or no L'Hopital. In fact, even if L'Hopital doesn't work, this will always work because this is the original definition of that limit. So even though in the olden days, there was no computer, there was no spreadsheet, so you can say it's tedious. It's no longer tedious. It didn't take me more than 5 minutes to get all this table and put it for you. It didn't take me more than 5 minutes. I don't need to know any L'Hopital's rule to find this limit. I can just tabulate it and I can see the limit. If it doesn't have a limit, it will be clear that it is not tending anywhere. If it has a limit, it will be tending to something specific that anybody who is not blind can see. That's it. So, does it tend to a limit? Does it not? If it tends to a limit, what is that limit? The limit here is 0. So, because the limit here is 0 and the limit here is 1, that is why the derivative of sine x is equal to cos x. That's all. And now I know from my own secondary school where my teacher didn't understand it and he just did wuru-wuru to the answer. That's what will happen. If you two go to teach without knowing it, you will just be shouting at the students when they ask you difficult questions. That's the thing. But the way out of that is to understand the thing fundamentally. So this is what you need to come up with. So just know that the first principle is easy. The first principle, the TDM ameliorated with computer, and it is not rigorous. So you can always find what the limit is. And the differential is the limit of a quotient. And because of the differential is limit of a quotient, you are always dividing with something. And that something you are dividing with is related to the argument. It is of the same order as the argument. So if the argument is a vector, then the thing must be a vector. If it's a scalar, it must be a scalar. But once a vector or a tensor, you are in trouble because you cannot divide by vector. So that is that. So it is that background that we need to cope with what we did last week. I can quickly just do you a review. And if now you are more active and you can understand what I was saying last week because of the preambles I gave you, that is again, that means that next week, when we now try to move it forward, we will not be struggling. And that is spending a week to achieve that is a week well spent in my own dictionary. So I don't care that we spend that time. If you didn't know it, you didn't know it. If you forgot it, you remember, go back to your 100 level and secondary school math. You will see that that's what they've been telling you all the time. But you were more interested in answering questions, and cramming can solve that problem. So you didn't really necessarily pay too much attention to the real issues of fundamental principles. So we are already familiar with the techniques of differentiation of scalar value functions with respect to scalar arguments. These subjects are defined in scalar domains. Here, x and h are real. The derivative f prime of x of the function f, which takes a real number, takes from one real set to the other, is defined as the limit as h tends to 0 of fx plus h minus f of x over h. We have been doing that. It poses no problem. This expression poses no problems as the definition as division by scalars is well defined. Division by scalar is well defined. Large objects, scalar arguments. Things become more complex when we handle tensors. A second order tensor contains 9 scalars. A vector contains 3 scalar members. The complication does not arise from the size of the objects themselves. Derivation of tensor objects with respect to scalar domains with some adjustment basically conforms to the rules as the above derivation of scalars. Division of a tensor by a scalar is accomplished by multiplying the tensor by the inverse of the scalar. So if you want to divide this tensor by 2, multiply that tensor by half. That is, you have done the division. You want to divide a tensor by 10, multiply that tensor by 1 over 10. The same thing. This operation is defined in all vector spaces to which our vectors and tensors belong. The derivative of a tensor function of a scalar argument with respect to a scalar argument, such as time, for example, can be defined as d dt is equal to the limit as h tends to 0 of t plus h minus t of t over h, which is the same thing as limit as h tends to 0 of 1 over h multiply that bracket. The product of the scalar 1 over h and the difference of the tensors are all defined, and they are tensors. The difference are tensors, for the scalar inverse is a scalar. Hence, the derivative of a vector or a tensor with respect to a scalar is a vector or tensor. So if you differentiate velocity, you get acceleration, which is still a scalar. If you differentiate a tensor with respect to time, you get the same tensor order with respect to time. So when there are large objects with scalar values and they are multiplying each other, last week I explained that d dt of alpha t will be equal to alpha d big T dt plus d alpha t dt. In this case, because multiplication by scalar is commutative, so whether you say alpha t or t alpha, it doesn't matter. So it doesn't matter whether you put t before alpha or alpha before t in any of these expressions, no problem. Proceeding in a similar fashion, with alpha being a real number, u and v being a vector, and s and t being tensor, all being functions of a scalar variable, all of them, even though they are scalar, vector, and tensor, they are functions of a scalar variable, and they are functions of a scalar variable t. The results in the following table hold as expected. The simple rule, when obeyed, allows us to gain proficiency and transfer scalar knowledge to tensors. Don't be fooled by symbols. They are overloaded. Because, for instance, when you add one tensor to another or vector to another, it's not a simple addition, because the vector has three things. So addition of 2 vectors, you are doing 3 additions. In addition of 2 tensors, you are doing 9 additions. So it's overloaded. The addition is not just as simple as you were doing before, but if you are careful, you will not make any mistake. So last week, I explained this. I gave you a puzzle here. I want to give you the puzzle again to be sure that you are awake. So answer this puzzle here. Let me just put it in writing so that it will be easy for me to follow. Answer the puzzle. So what is wrong with the first one? And how do you find the remaining 3? What's wrong with the first one? There's something wrong with the first one. Given that A, B, and C are tensors, what's wrong with the question d dt of A double dot B double dot C? There's something wrong with it. Can you tell me what? Admin, I don't think the class is hearing me. Okay, Babalola had. Okay, good. Is it possible to take the inner product of A and B and take his inner product with C? Don't you know that once you have inner product of A and B, the answer is already a scalar, and you cannot be talking of inner product of a scalar with C? So inner product of three tensors is like that is not defined. Yes, Ogochukwu, you are right. It's not defined. So that's the puzzle in the first one. What about DDT of A, B, C, where you take the product of A, B, and C? The product of A and B is a tensor, and you can also take the product of that product with C. So what would be the answer there? DDT, if all of them are functions of T. We can see the answer. Can you tell me what is important about that result? What you must not change? There's something you must not change, because if you change, there will be a problem. There's something about that answer you must not change. Good. Olajide says, and Ola Tomiwa, then Olamide, all of them, you can see that we must retain the order. If we retain the order, no problem. And that is what happens in the other things. As long as we retain the order, there's no problem. So this page is okay. So we can go on. So we now got some results from the constancy of the identity tensor. We got some results from there. And then there are more things. I believe that what we did, nothing really was that difficult from that point on. It is the lack of that background that made you, everything was basically straightforward. For example, here we say the identity tensor will give you 0. If we give you the annihilator tensor, for instance, if you have, if you look at the matrix expression of the identity tensor, is 1, 1, 1 on the diagonal. If you differentiate 1 with respect to T, you have 0. So all the things on the diagonal become 0 like the other thing. So it becomes the annihilator tensor. So if you differentiate every one of them with respect to T, you are going to get the annihilator tensor. So there's no problem with that. And then, since the product of a tensor and its inverse is equal to the identity tensor, and the derivative of the identity tensor is the annihilator tensor, that means that the derivative of the product is simply equal to the annihilator, which is 0, which is the 0 tensor. So with that, we can reach the conclusion that the S inverse dt is equal to minus S inverse ds dt S inverse. That is it. And the same thing can happen on both sides. So we can say that ds dt is equal to minus S ds inverse dt S. So these are conclusions. We are still looking at a situation where the argument is a scalar. There are still a lot of conclusions to be taken, even when the argument is a scalar. An orthogonal tensor is such that when you multiply it by its transpose, you get the identity tensor. And consequently, we can show that this kind of tensor, which is differentiating the orthogonal tensor and post-multiplying it with the transpose of the orthogonal tensor, that the tensor you get is a skew tensor. And if it is a skew tensor, we prove it here that it's a skew tensor because it's equal to the negative of its transpose. So anytime you see this kind of combination, it is a skew tensor. And because of that, if you apply a rotation to a vector, that is, let R0 be the function of space that is contained within this top. So if you apply that rotation, you can differentiate with respect to the new position, differentiate with respect to t. If you differentiate with respect to t, this is still all that we have here is the r dt r naught. We only omitted the functional relationship with this. That's all we have removed here. We didn't carry that along. And we are also here changing this r naught to r inverse r. So if you see r inverse r, and because r is a rotation tensor and a rotation is an orthogonal tensor, r inverse is the same thing as r transpose. So r inverse is the same thing as r transpose, and this one gives us the tensor. This product gives us the tensor we said must be skew. We call it omega. And if it is skew, it has an axial vector. When it has an axial vector, we call the axial vector omega. And then instead of saying omega r, we can say omega cross r, showing that there must exist an omega, and we call that omega angular velocity. So once you are rotating with respect to time, then you have an angular velocity, and every location there can be found by taking the velocity of every location can be found by taking the angular velocity across the position. So that is what we are saying here. That's a consequence. Here we are still differentiating with respect to time, which is a scalar function, and there are things we can obtain from there, and then we can go on. The next thing is magnitude. Magnitude of a tensor, we define magnitude as the scalar magnitude of a tensor as the square root of the inner product of the tensor with itself, which is the same as the trace of the tensor multiplied by its transpose. That is what is the inner product of the tensor with itself. And then if you do that, and because inner product is reversible, the trace of AT is same as the trace of ATA. So because of that, we are able to now therefore say that this scalar function, which is the square root of A with in an inner product with itself, is what we mean by the magnitude of A. So that phi squared is A times A inner product A. So if you differentiate this scalar equation, you have that this is 2 phi the t, and that is the A dt inner product A and A inner product A dt. Because of commutativity, that's same as 2 the A dt inner product A. And this means that you can now therefore say that d dt of this is simply the same thing as 1 over phi. 1 over phi, which is phi by definition is just the magnitude, 1 over phi, the A dt inner product A. So which is the same thing as the A dt, because A inner, this quantity here is, the quantity here is a magnitude and it's a scalar. So it doesn't matter where you put it, can be used to divide any of them. So this is just a convenient way to express it. There's nothing sacrosanct about expressing it this way. So the A dt is still a tensor, so we can take a scalar product with A and divide the second part with the magnitude of A to be consistent here. So that is another consequence of we are able to find from there that d dt of the trace is the trace of the d dt. That is the conclusion there. So examples, 3 tensor invariants. We can look at we have done the trace. Then we can look at the second invariant, which is, we can look at the second invariant, the trace of the cofactor. The second invariant is not a linear valued function of the tensor argument. However, we have the expression AC, that is the cofactor of A, is the inverse transpose of A multiplied by the determinant of A. So that the trace of it, the trace of it is the trace of this whole thing. So if you want to differentiate it, you have to say, since the trace of the derivative of a trace is the trace of the derivative, so you have this. But as we said, it's not a very useful quantity. But we can go to the third invariant, which is the derivative of the third invariant, that is the derivative of the determinant, is of momentous importance. This is the basis of the Liouville's theorem that we'll look at when we are doing continuum flow. And then the third invariant is not a linear function, so we can do the differentiation here. And when we when we looked at this last week and we reached the conclusion that is simply the trace of this quantity multiplied by the triple product of AA, AB, and AC. So, and that is the same thing as determinant of A divided by ABC. So that is, and if you bring the ABC on the left-hand side out there, so you can see that it is this quantity determinant of A. We didn't have difficulty with this. It was only coming because of the difficulty we were having with the other stuff that we were doing last time. So, what else did we do? Vector and tensor arguments. When the domain of differentiation itself is made up of large objects, when the argument is made up of large objects, the task of differentiation becomes more demanding. And those problems are not just academic, they are real. Such problems are standard in continuum mechanics. For example, the strain energy density is a scalar, yet we can obtain strains from it by differentiating with respect to the stress. We are dealing here with differentiation of a scalar function, with differentiation of a scalar function of a tensor, that is stress. The velocity gradient, here we are differentiating a vector field defined on the Euclidean space. So the vector is a function of a vector, because the Euclidean point space, when you are, for the purpose of differentiation, is like a, because every point there is a position vector. So it is a vector function of a vector, and that will give you a tensor. So you are differentiating a vector with respect to a vector. So this is where the problem is, the problem I've been talking about since the beginning. Vector and tensor arguments. This page is all error. So everything on this page is wrong. So don't just quote it because it's error. I'm just trying to tell you what not to do. When we're in a vector domain such that x and h are vectors, the derivative f prime of the function is not properly defined as f prime is the limit at h tends to 0 of f of x plus h minus f of h over h. Because this formula creates several problems. For example, 1, division by vectors is not defined. 2, there are many ways h can approach 0. So similar problems arise when the argument is a tensor. So this, we cannot just expand what we knew about scalars. You cannot just expand it this way to tensors or vectors, because division by or vector is not defined. Therefore, the approach to this challenge is twofold. First, that vectors and tensors live in their respective Euclidean vector spaces with the concept of length already defined. The Euclidean vector space that we are talking about is that magnitude is defined. For vectors is defined as the square root of the vector dotting itself. For tensors, it is the square root of the scalar product of the vector with itself, of the tensor with itself. That's why we say they are in Euclidean spaces, because the idea of a magnitude is defined. We are going to use that idea of a magnitude to create definitions for derivative. And we will show that that definition for derivative is a superset of the definition we already know. It's not something different. If everything degenerates to scalars, we are going to recover our origin. It's not, so the definition we are going to give is not contradicting the definition we had before. So we'll so define it that it does not contradict anything. Use the above to extend the concept of directional derivative to include the derivative of any object from any given Euclidean space with respect to objects from another. We're going to use the concept of directional derivative. Such a generalization is what is called the Gateau differential. We will now introduce the Gateau differential. I couldn't introduce the Gateau differential until I reminded you of your understanding of differential from first principles. Once that is clear, you will see that when we introduce this one, you can see that it is simply a small extension of what you already know. It's not really difficult. But it will be difficult if you forgot the first principles definition of derivative, and you are just depending on your formula that you have cracked. If you are depending on just the formula, this will be very difficult. But if you understand the meaning of derivative in the old sense, then there's no difficulty here. The concept of limit and continuity carries naturally from the real space to any Euclidean vector space. So we are now expanding it. We can say that let V naught be a vector and W naught be another vector. So both of them are in different vector spaces. So one is in the vector space V, the other one is vector space W. We can say that the limit as V tends to V naught of the vector of the function of a vector argument. This is now a function of a vector argument. It can be a tensor function of a vector argument. It can be a scalar function of a tensor argument or a vector argument, and it can be a tensor function of a vector argument. But in this case, we are talking of a vector function of a vector argument is equal to W naught. Means if for any pre-assigned real number, we are still dealing with pre-assigned real numbers, even though we are no longer in the real space. Because what we are going to use to compare will be magnitudes. So the magnitudes are real, even though we are talking of vectors. No matter how small epsilon is, we can always find a real number delta, such as the delta neighborhood. The magnitude of FV minus W naught, it is the magnitude that will be compared to epsilon, provided we're in the delta neighborhood where the magnitude of the difference between V and V naught is smaller than delta. The function is said to be continuous if FV naught exists and FV naught is equal to W naught. If you go back to the definition of the scalar function of a scalar argument, you will see that we have just done everything the same way. The only thing now is that the meaning we are giving to this is no longer just absolute value. This straight line brackets is no longer talking about absolute value, but it's talking about magnitudes. Because in the case of real numbers, we are talking about magnitude, but the magnitude is just the absolute value. Here, the magnitude is something bigger than the absolute value. You get it by taking the scalar product with itself and taking the square root of it. So that is what the difference here is. So there is not a lot of difference when we are talking of continuity and when we are talking of limit and continuity. So when we get to the differential, we can now introduce this quantity which we call the Gateau differential, and it is simply the limit as alpha tends to 0 of f of x plus alpha h. So you are still moving away from the point with an alpha multiplied by h. So h is still the same. If x is a vector, h is a vector. If x is a tensor, h is a tensor. But the alpha here is a scalar quantity. Now, so you see that if alpha is 0 here, we are at the same point because f of x or plus 0h is the same thing as f of x. So we are only going in multiples of an alpha. So we are multiplying by scalar. And if that scalar is 0, then we are at the point. So we can formulate this quotient and we are dividing not by anything else but that scalar. So what is tending to 0 is that scalar. So when we do that, this is the derivative of f of x plus h at f of big X evaluated at x plus alpha h, given that alpha is equal to 0. So this is the definition of the Gateau derivative. And if we focus our attention on the second variable h, where we allow the dependency on x to be as general as possible, we shall show that while the functional dependency on x can be linear or non-linear, the above map is always linear in H, irrespective of what the Euclidean space we are mapping from or into. And it is called the Gateau differential. So this page defines for us the Gateau differential. And I am getting this far. I want you to go home and let this sink into you because we are going to say more about it in the next lecture. We have only 5 minutes to go. So let me just, so the proof of the second equation term. So the second equation above is not obvious. That is this one, that this is equal to this one. It's not obvious. It can be shown by remembering that the scalar formula for derivative, by remembering the scalar formula for derivative and treat this function on the right-hand side as a scalar because it is a function as a function of alpha, as a scalar function. If we do it as a scalar function, everything becomes clear because you see that dB alpha of phi alpha is the limit as delta alpha tends to 0 of this. This is the definition from the scalar point of view. And if you substitute this, for that, you will see that it becomes the limit as delta alpha tends to 0 of f of x alpha plus delta alpha h and so on. so that the alpha of f of x plus h is the same thing as the, by the time you work this out, you find out it's the same thing as the Gateau differential that we defined on the previous line. So what we are doing there is we are explaining that this quantity, this is from here to here is the definition of the Gateau differential. We are just expressing that we are proving that it is equal to this by what we have on page 33. That is all we are proving on page 33. So there are two equalities here. One is an identity. The identity is a definition. So we are saying that this quantity you have there, this quantity here is simply a symbolic representation of it. Doesn't mean anything else. So there's nothing to understand there. We are just using this symbol to represent this. But this is what we prove on this page. So you have to go back again and look at this page, and you see that it shows that this the alpha of f of x plus h, f of alpha h, is the same thing as this. So the last thing we do today, if time permits us, we have 4 minutes to go. The last thing we do is to go back again and see whether all we are saying makes sense when we are dealing with real functions in real domains. We have defined the Gateau derivative. Suppose we are not looking at a scalar, a vector function. We are not looking at a tensor function. We are just simply looking at a scalar function of a scalar variable. Does it still make sense? Well, if it's a scalar function of a scalar variable, what will it look like? This f here will be a scalar. This x here will be a scalar x, and this h here will be a scalar h. Everything here will be, everything that is in bold here will be in ordinary italics. So there's no, so if we do that, so that means that we then have that if instead of h we write the x, this equation is true. If instead of h we write the x, so that we limit as alpha tends to 0 of f of x plus alpha h. We have changed alpha h now, we have changed h now to be the x. Okay, so which is equal to d the alpha of f of x plus alpha the x. So all we need to do is let alpha the x be delta x. If on this line we change everywhere that alpha the x occurs to be delta x, that means that when the x occurs alone, it becomes simply the x over alpha. So or alpha itself is delta x over the x. So instead of alpha here, we are going to write, delta x over the x. So we are going to have it, and that dx is what is multiplying here, if you work it out. So everything now becomes, so by the time we work it out, you can see that our Gateau differential becomes exactly the same as the ordinary differential when everything is real. When everything is real, you know that this is the differential of f. If you are talking of a real function of a real single variable, this is the differential. So our Gateau differential is an ordinary differential if everything in it is simply scalar. From which it is obvious that the Gateau differential is the generalization of the well-known differential from elementary calculus. So since it's a generalization of the well-known differential from elementary calculus, so we can use it without any problem, because we know that if everything degenerates to scalar, we get our familiar relationships. But if it is now a vector and tensor, we have new powerful tools to deal with the problems that we would have had. The Gateau differential helps to compute local linear approximations of any functions, linear or non-linear. I will stop there, and by next class, we will start on page 35. So since we have gone 2 rounds on the first few pages, I don't think we need to worry again. Please, class, in order for us to not be dull, to be smart with the class next time, please read this again, look at all the issues, look at all the arguments, and if you have questions, please bring the questions to the class. I will answer your questions in the next class, but I hope you won't even have any difficulties any longer, because I've spent time to go back to the basics, and I hope I'm carrying you along now. So it is time to say bye-bye now. So goodbye, class.